Okay, let's get started. Today we'll get into another aspect, a huge aspect in computer architecture actually, memory. One could argue that memory is one of the biggest bottlenecks today in designing microprocessors or systems. But before that, reminder, April 2nd you have homework 5, and we have already covered a good chunk of this. We'll cover memory and caches so that you can do your homework. And there's a virtual memory question. We'll likely not get to it, but you should still solve it because you already know those concepts from 243 or 213, right? Did you already look at the question? It's essentially figuring out what are TLB hits and misses. And you already covered that in 213, 243. Okay. Lab assignment. This is your new exciting lab assignment. You have a C-level simulator, high-level simulator, as I told you before, and you're going to implement caches and branch prediction. First step, you should really understand the simulator. As with any simulation, a simulator that you're given, the first step should really be understanding the simulator. You don't want to do something without understanding the simulator. Well, I don't know how you would do it, but it's dangerous to just jump into the simulator and modify it before understanding what happens in the simulator. So to aid this, TAs will go over the baseline simulator in the discussion session. So I would very strongly encourage you to attend the discussion sessions. Nothing is required in this course. You don't need to attend the lectures even. You can watch them online if you want, but discussion sections, you won't be able to watch them online. So this will give you a very good base to start. Otherwise, you'll have to figure out someone else's code on your own. Even though the code is very well documented, at least by my standards, a lot of the simulators are actually not this well documented, in my view. Is that right, Chris? I think so. Okay, good. It's his baby, so even though that's the case, you will learn a lot better if you actually go to the discussion sessions and somebody tells you what's the structure of the code and what goes on. Okay, and we have an extra credit assignment too. You will do cache exploration. And you'll try to get high performance with optimized caches, and we'll do the same thing. We'll evaluate the best 3 designs. Actually, it could be best n designs if all n designs happen to be within X% of each other, if you will, right? Just like we did last time. 4 people won the extra credit. So hopefully this should be fun, and hopefully you will see how easy it is to do this exploration at the high level, if you will, at the C-level simulator, because you don't need to model every single gate as you did in Verilog. Right now you're really modeling at a high level what the processor does without modeling every single gate. It's a logical simulator, if you will. And you can still get the timing by changing the parameters of the cache. Right? You can still, well, not timing in terms of cycle time, but in timing in terms of number of cycles it takes to execute a program. So if you change the replacement policy of a cache, which we will talk today, you will see the effect of that on performance, on the number of cycles it takes to execute the program. And hopefully that'll be much faster than you could do in Verilog. Of course, what you're losing is now, because you don't have a gate level design, you will not get the cycle time, right? In fact, in this high level simulator, you can do things that could affect the cycle time significantly. And if you do not know what you're doing, you may get a number of cycles with that cycle time, and you could double the cycle time of the processor, right? So you've got to be careful when doing performance evaluation with this simulator, because it doesn't really give you what the cycle time is. Right? So optimizations you do, you need to be careful. You need to think about how they affect the cycle time. So for example, you could design a huge cache, right, that reduces the number of cycles you execute, because you're not really modeling the cycle time, but you could assume that you access that cache in 1 cycle in this simulator, but that would be a wrong assumption potentially, right, for a target cycle time. Or you'll need to reduce the cycle time to be able to achieve that. Okay, so hopefully when you're doing this assignment, think about like what are the pros and cons of this kind of simulation. Okay? Okay, actually there was one question that appeared over the weekend. Somebody was turning in their lab late, and they asked, can you still get extra credit? Are you still eligible for extra credit if you turn in the lab late? And absolutely, the answer is yes. because we don't really care why you turn in the lab late. If you happen to turn in a very optimized design by using your extra days, that's fine for us. Okay? That's fair. Right? Everybody can use extra days for whatever they wish. Of course, this is an optimization decision, again, on your behalf, because there's always the next lab, right? Do you spend time on the previous lab, or do you go to the next lab? Okay. Okay, I've already told you that. Exam solutions, TAs will finish going over those and pick up your exams today. Talk to us if you're worried about how you're doing in the course. I think some of you talk with the TAs. If you wish to talk with me, I have office hours, or you can email me to set up a time. And talk to us if you want to do more too. I know there are people on both ends of the spectrum. Okay, these are your readings. Just a reminder, we're done with basically a lot of things that people have tried to do to get more concurrency out of computation. We've talked about out-of-order execution, data flow, SIMD, single instruction multiple data execution, and VLIW in the last 2 lectures. And these are different execution models, if you will, that improve upon in-order execution. All of them improve upon simple in-order execution. And combinations of all of these are actually employed in today's processors. Not data flow at the ISA level, but data flow at the microarchitecture level. SIMD we've seen. We have vector instructions. GPUs are SIMD machines that are not programmed exactly like SIMD. VLIW processors exist, like digital signal processors, or even general purpose processors were attempted to be built in VLIW fashion, like IA64, as well as Transmeta's underlying implementation was VLIW, and they converted the x86 binaries into VLIW with a software layer. So all of these are real, they exist, and you should know the trade-offs associated with them. Today we'll cover something that's common to everything else. Basically, we've covered computation, if you will. We're going to cover the memory hierarchy. And you're already familiar with some of this, hopefully, right? Yes?
Are we sort of just switching gears and going away from computation and just going towards memory?
That's right, yes, essentially. And we'll examine the coupling between them also. Well, actually, here's the coupling between them. So being an idealist is good. So when you think of a machine processor, you can think of it in 3 components. Actually, I showed you this picture in a different way earlier. I showed the processing unit, data supply, and the instruction supply. And we've covered essentially what happens here, right? And ideally, what you would like here is no pipeline stalls. And we've covered different ways of achieving this. Perfect data flow. Execute an instruction when its data is ready. We'd like zero-cycle interconnect, zero-cycle communication between the instructions. We haven't covered how to do that, but that's if you want to achieve very fast execution, ideally this is what you should do. Communicate the data that an instruction needs right away to another instruction, right, in zero cycle. We would like enough functional units. If we would like to exploit parallelism in the program, we need to have enough functional units, right? If your VLIW instruction, if you want to support a 100-byte VLIW instruction, you should have 100 functional units. And ideally, we would like zero latency compute, right? Wouldn't that be nice? So it's good to think about how to achieve this ideal when you're designing the pipeline. And we try to do this, at least some of these, in the earlier parts of the lecture. But an important part of achieving fast execution is supplying instructions to execute into the pipeline. And we've seen this with branch prediction, right? We want a perfect control flow going into this pipeline. And that's what you would like in an ideal instruction supply. And also, ideally, you would like to supply the instruction at zero-cycle latency. You don't want to get a cache miss, if you will. You would like infinite capacity. You don't want to get a cache miss. And you want zero cost from the supply. Data supply is similar. You'd like to get the data you need when you do a load or store at zero latency. You would like infinite capacity here so that you don't miss, if you will. And you'd like infinite bandwidth. And we've seen this in vector processors, right? Vector processors, because you're executing many the same operation on many data elements, you'd like to be able to load all of those data elements at once. And that's a bandwidth problem. You'd like to, in a sense, latency is less of a problem over there because you have so much parallelism, but you need to supply the data at the bandwidth that you're executing on. And you would like zero cost. So we'll cover, we kind of covered this part. Now we're going to look at instruction and data supplies and how to design that. That's the idea of a memory hierarchy. Let's cover that. If you look at memory in a modern system, these are the cores that have the processing units. And if you look at the chip, most of it is really dedicated to supplying instructions and data to those cores. In fact, this is one of the chips. This is AMD Barcelona. It's an old chip by now, and this is one of the chips that have relatively high fraction of cores, if you will, in terms of chip area. So you see that there, and here I didn't even show the L1 caches, and hopefully that'll become clear at the end of the course. L1 caches are very tightly coupled with the cores because their design requirements are really dictated by the pipeline. Because you want to get the data right away from the L1 cache. Ideally in one cycle. Well, ideally in 0 cycle, but take that as one cycle. So we have levels of cache hierarchies, L2, L3. And when a core accesses memory, if the data is not in its caches, it needs to, when a core does a load, it needs to go through the memory controller and access the DRAM banks, and data needs to be brought into the caches, all the way into the cache hierarchy. And we'll see why we have these hierarchies. So ideal memory, as I told you, we want 0 access time, 0 latency, infinite capacity, and 0 cost. And infinite bandwidth to support multiple access in parallel. So how do we try to achieve this? The problem is these requirements oppose each other, right? So you cannot build a large capacity memory at low access time. Why? Because bigger is slower. If you want to increase the size of your memory, well, let me go over this. It takes longer to determine the location you were trying to access, right? Because you have an address, you need to decode the address, and as the size of your memory structure is larger, the address you need is larger, which means that decoding takes more time. The other problem is faster is more expensive. We want 0 cost, but fast, again, that contradicts. Those two things contradict each other. And this is dependent on the memory technology. And we will see 2 technologies very soon, static random access memory and dynamic random access memory. Static random access memory is faster, but a lot more expensive than DRAM. Higher bandwidth is more expensive because you need to do things to get that higher bandwidth, right? In for example, the Cray machine that we studied earlier, you need to add more banks. And adding more banks makes the memory more expensive as opposed to a single bank design. Right? Why? You need to figure out which bank to access. You need to have control logic to ensure that accesses are scheduled. Right? You could have more ports. You could get high bandwidth that way. You could increase the frequency. Or you could have it use a faster technology. All of these make higher bandwidth more expensive as well. So let's take a look at these memory technologies. This is DRAM. You've seen DRAM versus SRAM, right? In your previous courses? Yes? Okay, so I'll go through these relatively fast. And this is essentially where your charge is stored, right? It's a capacitor, if you will. We'll add more to it soon. Capacitor charge state indicates the stored value. Whether the capacitor is charged or discharged indicates a 0 or 1. And it consists of one capacitor. That's DRAM. Well, not quite. You need to be able to access that capacitor, right? So you need to have an access transistor, if you will, that enables you to discharge the capacitor so that you can read whether the capacitor is full or empty, if you will, charged or discharged, right? And we will see what these are. Basically, you've seen it before. This is a bit line. When you enable access to this capacitor affects the bit line, and you can sense whether the bit line is a 0 or 1. Right? Well, there's one problem with this. Capacitor leaks through this RC path, if you will. Capacitor is connected to the bit line, and there's leakage that happens, which means that this capacitor loses charge over time, and DRAM cell, this is a cell, if you will, that stores. A memory cell is the single unit of storage in memory that stores 1 bit. And this cell loses charge over time, which means that you need to refresh it if you want to keep the charge there. So in this type of memory, you need to have a controller that periodically refreshes the charge in the cell. Basically reads this capacitor and pre-charges it again, if you will. Okay. So that's one downside of DRAM memory. We'll see the upside. Upside is very compact. It's very dense, if you will. It's only 1 transistor and 1 capacitor. So you can have very large densities. And it's cheap, partly because of that reason. The second major technology is SRAM, static random access memory. It essentially consists of 2 cross-coupled inverters. And this feedback path enables a stored value to persist in this memory cell. And you've seen this before. 4 transistors are needed for storage. But then if you want to access this, you add 2 more transistors. And there are variants of this also, but this is the most common SRAM cell, if you will. Now you have, well, why 4 transistors? Because an inverter is 2 transistors, right? And we add 2 more access transistors, if you will, to access the cell. And you have bit line. This is the stored value, if you will, and bit line bar. This is the complement of the stored value because you have the inverter. And you access the cell by enabling both transistors and reading the stored value and stored value bar over the bit line and differentially sensing it downstream. Okay? So this uses 6 transistors. Now let's build a memory array out of this before we go into the trade-off between SRAM and DRAM. This is a bank organization for memory. Let's look at its operation. And this is independent of the technology right now. The way you build a memory is you take one of these cells and you replicate it in a row, if you will. So this is called a row. And a row could have, depending on the size you want, let's say you could have 1,000 of these cells, if you will. Then your row contains 1K bits. And you have also columns. This is your row. And you have a bunch of rows put together in a 2-dimensional storage array. So essentially you have rows and columns of memory. And you could define, let's say, each column to contain a number of these cells. For example, if you want to do a word access, you could define a column to contain a word access is 4 bytes, let's say. 4 bytes, right? So this is generic memory bank structure. Rows and columns. It's a 2-dimensional storage array. So how do you access it? Basically, you can have an address register that stores the address. And with the most significant bits of the address, you figure out what the row is. Right. So this is your address, if you will. And let's say these are bytes in your column. These bits you use in your address to select which byte in a column you take. And these most significant bits in the address determine your row. The middle bits determine which column in the row that you want to take out. So you take this row bits, if you will. It goes through a row decoder, gets decoded. And once it gets decoded, what it does is it enables the row select, or word line, if you will. This is also called the word line, of the cells in the same row. So now you can read all of the cells within this row. Right? All of them drive their bit lines, if you will, down into the, well, these are the bit lines shown here, into the column decoder. And the column decoder's job is essentially to use the column bits to select which column should be read out of the memory. Make sense? So the operation is very simple. First, you decode the row address and drive the word lines or row select lines. Selected bits in a row drive all of the bit lines, so you read the entire row. And there needs to be some amplification of row data because usually these cells store very little charge. So you need to amplify it to figure out what the data is. And the column decoder decodes the column address and selects a subset of the row and sends the output. And at the end, there's an operation called pre-charge. Bit lines are because once you read, you've disturbed these bit lines. Now bit lines are charged with whatever you read, so you pre-charge the bit lines to their original state, if you will, so that you can, when you read the data, they will be affected next time. You've seen all of this before, right? Yes? Okay. So this is independent of the technology. If you look at SRAM, basically these cells consist of these, right? And this is a typical SRAM array. Why do you have this two-dimensional organization? Why not read only one column? Why not have only one column? Well, you decide this organization to minimize the overall latency, right? If you have a fixed size memory, you don't want to have only one column because now your address row decoder takes too long, right? You usually equalize this array size, the size of the rows total and the size of the columns to minimize overall latency. Okay, I will not go through this in detail, but read sequence is very similar to what I described here. I guess you read the entire row, and we have 2 bit lines. There's circuitry here that senses the 2 bit lines and essentially selects the column, which are the sense amplifiers and the mux here, and then you pre-charge all bit lines. So what is the access latency of this? Basically, access latency is dominated by decoding the row address to enable the word line, and also pulling down the bit lines, getting the data down into the sense amplifiers here. And when can you do the next access? What is the cycle time? It's dominated by basically you need to decode the address, get the data through the bit lines, and also pre-charge the bit lines for the next step. Yes?
Was the general idea you want to break it up so that you're decoding both the row address and the column address at the same time?
So yes, you could do that, but then it's serial in a sense, right? Because you have to get the row first to be able to mux out.
Okay, sure.
So the critical path is not really the decoding of the column address. The critical path, decoding of the row address, getting the row out, and selecting the right column. So the reason you make this more or less square is to minimize overall latency. You don't want the decode of the row address to dominate the latency. That could be very large. Yes.
Is that the only metric you use to decide the row size and column size for the bits and array? Because do you only consider how long it takes for row address and column address to do it?
Depends on what you're optimizing for, right?
Or could you be optimizing for getting chunks out together, getting certain chunks of memory out together?
So
not just one word read, but maybe you want multi-word read.
yeah, if you want to do many words, then yeah, you can actually make it larger, right? So if you're optimizing for latency, yes, this is what you would do. But this wastes energy also, right? If let's say your row is 4 kilobytes and you want to read only 4 bytes. Now you're activating the entire row. You're pulling down all of the bits from that row, even though all you need may be just 4 bytes, right? You've optimized for latency, but that's bad for energy. So there are a lot of design choices. This is a complicated design. Okay, DRAM is very similar. Your bit cell array is like this. Your cells are essentially 1 transistor, 1 capacitor cells. Now here I've shown you a little difference. Here we've supplied both the row address and the column address at the same time, if you will, to the SRAM array. We've decoded the column address. Well, you could have an address register here. You supply both of them at the same time. Most DRAM chips, you first supply the row address and initiate and activate, if you will, and then you supply the column address. So you divide N versus N. Can anybody guess why? To save pins, exactly. Because DRAM is off chip, right? And pins are extremely valuable. If you supply, let's say this is 32 bits. If you supply 32 bits at the same time, you're wasting 32 bits. But you could multiplex over time and use only 16 pins. Let's say this is 16 by 16 array. you first supply the row address, 16 pins, through the 16 pins, and then that gets latched in DRAM. And while that row address is being decoded, in the next cycle, next DRAM cycle, if you will, you supply the column address. And that's the only reason. That's the why you would do this. Whereas on chip, SRAM, you don't have that constraint, the pin constraint. Okay, so other differences, well, we've already talked about this. Bits stored as charges on the capacitance, and bit cell loses charge when it's read. Not only when it's read, but also loses charge over time. Which means that after you read the bit cell, after you read a row, so when you read a row, you destroy all of the contents of the row. Which means that after you read it, you need to restore the row. And over time, you need to do a refresh. A DRAM controller must periodically read all rows within the allowed refresh time, such that charge is restored in cells. Otherwise, you will lose all charge in DRAM. And for existing DRAM, the specification is 64 milliseconds. So every 64 milliseconds, the DRAM controller needs to refresh every row. So you could see that this could be a big energy cost, right? If you have especially large amounts of DRAM. Even if you're doing nothing on your system, you need to do this if you want to maintain your memory state. Okay, so read sequence is the same as DRAM. The main difference between DRAM and SRAM is how to do the sensing. So you have a sense amplifier that amplifies this bit line here. Okay, I will not go into too much detail here. We'll come back to this when we cover main memory. So what are the trade-offs? DRAM is slower access because of the capacitor. It's higher density, requires only one transistor and one capacitor. And it's lower cost because of higher density and manufacturing it is manufacturing process. It requires refresh, one downside, which consumes power, performance, because when you're doing refresh, you cannot access that bank, right? You cannot access, you need to refresh that row. So refresh is essentially activating a row and pre-charging it so that the data is restored. And manufacturing DRAM requires putting capacitor and logic together. So this is different from the logic process that we've been used to, right? In none of your labs you put capacitor anywhere, right? At least not in 447 on chip. SRAM is faster access. There's no capacitor. It's lower density though. You have a 6-transistor cell. It's higher cost, partly because of this. There's no need for refresh. Manufacturing is compatible with the logic process. So, because of these properties, SRAM and DRAM are used for different things. Well, let's go back to the problem. We said bigger is slower, right? And smaller is faster. So you want to make the close-by memory fast, if you will. So if you look at SRAM, the 512-byte SRAM today takes sub-nanoseconds. A kilobyte to megabyte SRAM takes approximately a few nanoseconds, if you will. DRAM, a gigabyte of DRAM takes perhaps 50 nanoseconds. These are just ballpark numbers. And hard disk, a terabyte of hard disk takes on the order of milliseconds, right? And faster is more expensive. If you look at SRAM, you pay $10 per megabyte. And these numbers change over time, of course. DRAM, you pay $1 per megabyte, and hard disk, you pay less than $1 per gigabyte. And add less than here. Because what happens is these sample values scale with time. The cost reduces over time. Okay, other technologies have their place as well, and we're not going to talk about that. There's flash memory, you may have heard of, that is being used. And there's some other upcoming memory types like phase change memory that operate on different principles. Basically, you have a material, you change the state of the material by heating the material, by melting the material. And the state of the material, whether it's amorphous or crystalline, tells you whether a 0 or 1 is stored. So it's a very totally different technology from what we have seen here. So you could imagine these other technologies potentially having their place. So flash memory is slow. Flash memory is another charge-based memory like DRAM, except the charge is not stored in a capacitor, but charge is trapped in a floating gate, if you will. Okay, and you can, if you're interested, you can place them. So flash places here, and phase change memory actually places between DRAM and flash in terms of its characteristics. Okay, so we said bigger is slower and faster is more expensive, but we want both fast and large, and hopefully at low cost. But we cannot achieve both with a single level of memory. We cannot design a huge thing, if you will, huge bank that is fast. So that's why we developed the idea of a memory hierarchy. Have multiple levels of storage, if you will, that get progressively larger and slower as you get farther away from the processor, and manage this in an intelligent way such that most of the data that the processor needs is kept at the fast, small storage. That way, hopefully, you can get this illusion of fast and large memory while paying some cost. Okay. So this is the idea. Basically, you have fast, small memory, let's say SRAM, and you have a huge but slow memory, big, and you basically move the data such that the things that you access or that you will access soon stay here, so that you don't need to incur the latency of going into the slow memory. Make sense? And you could imagine having multiple levels, and we will see that there will be multiple levels because, and we will see the reason for it soon. Okay. Well, fundamental trade-off is fast memory is small, large memory is slow. That's why we have this, right? So the memory hierarchy actually includes the register file as well. Right? So in the CPU, we have the register file. You have a small cache that backs it up, and this is really managed by the compiler. And then you could have multiple levels of caches here. The cache caches the data that you touch in main memory, and main memory is actually a cache for the hard disk. Right? And this part is managed by the operating system, if you will. Okay, so why does this make sense? This makes sense only if you could take advantage of this fast storage, right? If you never have the data you need in the fast storage, then in fact this is worse because now you're increasing your cost. You're adding more of these memories, so you might as well just go to the slow memory all the time. Right? But fortunately, things behave in a manner that has locality. Even people behave in a manner that has locality, right? One's recent past is a good predictor of their near future, if you will. So temporal, there are two kinds of locality which we will tie into caches. But if you look at yourselves, actually you were sitting here last time, right? So we will get back to that. For the temporal locality, if you just did something, it's likely that you will do the same thing again soon. So since you're here today, there's a good chance you will be here again and again regularly. And if you're not here today, for those who are not here today, it's likely that they're not going to be here next time again. And that's been pretty consistent so far, even within this class. Right? So that's the idea of temporal locality. Spatial locality, if you just did something, it's very likely you will do something similar related. So this is stretching the analogy a little bit. But for example, every time I find some of you in this room, you're sitting next to some others, and usually that's predictable. Right? Not always. Sometimes you change locations, but usually there's spatial locality in where you guys sit here. So let's apply this to memory. A typical program has a lot of locality in its memory references. And typical programs, when I say typical program, think about a program that's composed of loops, if you will. Temporal locality means that a program tends to reference the same location many times within a small window of time. So if you've referenced a data, it's likely that you're going to use that again. Right? This is why storing values in registers works. Right? This is the same principle. We're just going to extend this principle to caches. Spatial locality, a program tends to reference a cluster of memory locations that are close by to each other. So if you referenced memory location A, Well, if you look at memory like this, memory location A, it's likely that you're going to reference something around it soon. That's the idea of spatial locality. For example, if you're executing instructions have nice spatial locality, right? Because let's say you don't have any branches, it means that you're always going to the next instruction. And guess how the instructions are laid out in memory? You always do PC equals PC plus 4, right? Which means that if you referenced an instruction at program counter A, it's likely that, well, it's almost certain that unless it's a branch, the next thing you're going to reference is PC A plus 4. And then A plus 8, A plus 12. Similarly to array references, right? If you're traversing through an array, again, you have good spatial locality. What you're going to reference is what is next in the address space. Okay, so the idea of caching is to exploit these two kinds of locality. Temporal locality, how do you exploit that? Store recently accessed data in automatically managed fast memory. This is called a cache. The anticipation is that the data will be accessed again soon. And I already told you this works because of the temporal locality principle. And this idea has been around for a very long time. This is the first paper that talks about it, but things have been built even before this to exploit it. And you should read it. This is one of your required readings. It's only 2 pages. And it clearly explains what the idea is. The terminology is a little bit different, but the use is discussed of a fast core memory of, say, 32,000 words as a slave to a slower core memory of, say, 1 million words in such a way that in practical cases, the effective access time is nearer that of the fast memory than that of the slow memory. That's the idea of caching. How do you exploit spatial locality? Basically, in this cache, if you will, in this fast memory, store addresses adjacent to the recently accessed one as well. So don't store, so you recently accessed word A, don't store just that one, but store the things around it in the cache. And this is the idea of a cache block or a cache line. So you have a cache block or line that's bigger than what you just accessed, in the anticipation that nearby data to that block, to that word you've accessed will be accessed soon. Okay? So how do you do this? Basically, in a sense, if you look at your physical memory space, you can logically divide this memory into blocks, if you will. And let's say your block size is 64 bytes. So this is block 0 in physical memory, and block 1, and block 2. And when you access an address in a block, let's say you access this word in block 2, let's say this is 145, or I don't know, 145, let's say. It's probably closer to here. Don't just bring in the bytes or the word at 145, but bring in the entire 64-byte block that's associated, that this word falls into. Okay? So that's the idea of spatial locality. And we've already covered this. This is what IBM 36085 actually implemented. This is another one of the early papers on caches. It's a very clear paper too. Maybe we should put it up as a recommended reading. So what they had was a 16 kilobyte cache with 64 byte blocks. So 64 is a good number, actually. A lot of processors today use 64 byte blocks. Okay, so there's an analogy to this. I like books, so you can think of caching as caching books. The book in your hand is the book that you're processing right now, right? So that's the recently accessed book, if you will. And you usually put, you really have a hierarchy, if you will. You have books in your desk that are faster to access, assuming you're sitting on your desk. Well, sitting next to your desk. Hopefully you're not sitting on your desk. You could. But those books are faster to access, but your desk has limited capacity, right? You cannot put everything on your desk, all of the books that you're dealing with. So, which means that some books are at the bookshelf, which is bigger, hopefully. Some books are at the boxes at home, and some books are at the boxes in storage. So hopefully the books that you accessed recently are stored in your hands or desk, and you bring in books that you're going to access soon into the desk on your hand, right? So recently used books tend to stay on the desk. Hopefully your computer architecture books are there. Or books for classes that you're currently taking. Until the desk gets full. Once the desk gets full, now you have to decide which book to put to the bookshelf. And spatial locality applies here also, right? Adjacent books in the shelf could be needed around the same time. So if you have your computer architecture books together in your shelf, you could need all of them at the same time. After listening to this lecture, you want to learn about caches, and you want to look at different books, right? So you bring all of them to your desk. Of course, this works only if you've organized and categorized your books well in your shelf, right? And this is also true for computers. If you organize your data well in memory such that things that you're going to access together are in consecutive locations in memory, you get better spatial locality. Remember the row major versus column major access? If you're always doing row major traversals in your matrix, you'd better store that matrix in row major order. Because if you store that column major order, then you don't have any spatial locality. Make sense? Okay. Okay. So caching in a pipeline design, this is what I mentioned earlier. The cache needs to be tightly integrated into the pipeline. Why? Because you have this pipeline that wants the data very quickly from the cache. So ideally, you would like to access the cache in one cycle such that dependent operations do not stall or do not wait at all. Okay. This is called the load to use latency, if you will. Ideally, you would like to have load to use latency equal to one cycle. Which means that you cannot make this cache very large, right? But you want a large cache and still a pipeline design. Which means that you'd like to add more levels, if you will. A larger cache, but slower cache. You access the second level cache if you missed in the first level. That's the idea of the cache hierarchy. And this is exactly the reason why level 1 cache is really, the way I see it is, it's really part of the processor. It's less so part of the memory hierarchy, if you will. Because its design constraints are really the design constraints of the processor. How fast you want to make this processor dictates what kind of cache you will have at level 1. Whereas level 2, the decisions are more independent of what goes on in the processor, right? The reason is you would like to optimize your L1 cache to supply the data very fast to your pipeline. Okay? It's very important. Okay. So far I've assumed that you manage this hierarchy automatically, right? When you access some data in main memory, you bring the data into the caches automatically. That doesn't need to be the case, right? Well, with registers, it's not the case, right? There's no automatic management, right? The hardware, for example, when you access some words in main memory, the hardware doesn't decide, oh, let me put this into register 5. Automatic means transparent to the programmer. The programmer doesn't need to worry about it. Whereas with registers, some programmer needs to worry about it, right? The compiler writer needs to figure out, oh, this memory location should go into this register. So manual means programmer manages data movement across the levels. This is too painful. So if you expose these caches to the programmer, and if the programmer needs to manage them as different registers, for example, that's difficult to do. You could design a compiler to do this, but that's also difficult because, remember, the compiler, going back to the basics, compiler doesn't have dynamic information, right? Compiler does not always know what memory location will be referenced next, or referenced in the next few cycles. So it's too painful for programmers to manage on substantial programs, but this used to be the case. People used to move data from core memory to DRAM, well, DRAM memory to core in the 50s. in the early 50s. And this is still done in some embedded processors. This is the idea of scratchpad memory. It's not a cache, but it's a similar idea. You have, this is your processor, if you will, and you have a register file, and you have a little memory here, fast and small, with an address space. And you have this main memory. You can think of this as level 1 memory, if you will, and level 2 memory. And you have instructions in the ISA that loads from level 2 into level 1. And you can address them independently. And the programmer needs to do this. Turns out this is very burdensome for the programmer. But embedded processors, if you know your data very well, and it's predictable, and if you want to eke out the last amount of performance to minimize your energy, then some people are willing to do this. Okay, automatic, this is what a cache is. Hardware manages data movement across the levels transparently to the programmer. Programmer's life is easier. Remember, programmer versus microarchitect. Again, we're back to that same trade-off. Well, whose life is harder? Microarchitect's life is harder now, because they need to design this. They need to manage the data movement between different levels, if you will. But hopefully you'll get better performance. So usually you use a simple heuristic. Keep most recently used items in the cache. And we will see if that's a good heuristic soon. We'll see other ways of managing the cache. And the average programmer doesn't need to know about it. But if you want to optimize your program, you may want to know about how this management is done. Right? You may want to know the cache size, as well as what kind of policies are used to bring in data into the cache. Why? Because if you want to make best use of the cache, ideally you would like to keep the data within your cache such that you don't get any cache misses. So you may want to partition your program such that your data that you're operating on fits into this cache. So if you want to write a fast program, you actually may need to know the characteristics of how large the cache is and how it's managed in hardware. But if you want to write a correct program, then you don't need to know anything at all, assuming the hardware manages the cache hierarchy transparently to you. Yes?
When you say cache details being part of an ISA, does that mean, so when we decide something is a part of an ISA or microarchitecture, do we say the bare minimum that needs to be in the ISA or anything that helps to write a program? So I guess my question is, should cache details be part of the ISA or the microarchitecture?
Depends if you want to expose it, right?
Right.
So for example, today's ISAs have prefetch instructions that are exposed to the ISA. A prefetch instruction says prefetch this memory address into the L1 cache.
Right.
Which means that this cache is now part of the ISA. Right? Because there are operations in the ISA that operate on the cache. But you're not required to use them. Right? It's still automatically managed. Right? It's still managed transparently to the programmer, but if the programmer so chooses, they can use these prefetch operations. That's very different from this pure manual management. Here the programmer, if they want to take advantage of the scratchpad memory, they have to, say, move the data from the slow memory to the fast memory. Okay. So automatic management in memory hierarchy, this is the paper that you're reading, and you should still read it. I've already given you this part. But that's the concept of the cache, really. By slave memory, we already talked about the slave memory, right? Which is slave to a slower memory of 1 million words. By slave memory, I mean one which automatically accumulates to itself words that come from a slower main memory and keeps them available for subsequent use without it being necessary for the penalty of main memory access to be incurred again. It's nice writing, actually. You'll enjoy it. Okay, so if you look at the modern memory hierarchy, just to put all of this together, what you have is a register file that's small but fast and managed manually by the compiler or the assembly programmer. And you have this hierarchy of L1, L2, L3 caches and main memory, where data is automatically managed when hardware manages the caches here. And you have this other part of the highest levels of the hierarchy, if you will, that is managed through demand paging. Again, automatically. But some programmer needs to do it, actually. Okay. So let's briefly go over the performance analysis of this. I don't want to spend too much time on it because... Did you guys do this in 213? Yes? Okay. So you probably remember. At each... basically, there's an access time of each of these levels, right? For level I, you have an access time of Ti. And you have an overall access time that you get, let's call it the average memory access latency of the entire hierarchy that's longer than the closest level. Right? So when you're looking for a given address, you could either hit at one level or miss at each level. So for each level, you have a hit rate and hit fraction, if you will, or you could call it hit rate, and a miss rate. And if you add them up, you get 1. So your overall access latency is a recursive equation based on these levels. Basically, hit time of the first level times the fraction of times you actually hit in this level, plus the miss rate, what fraction of the time you miss in these levels, times the time to access the remaining of the hierarchy. And how do you calculate the time to access the remaining of the hierarchy? Again, that's a recursive equation. That's the hit rate of the second level times the time to access this level, plus miss rate of this level times the time to access the remaining part of the hierarchy. Okay? So you have a recursive latency equation like this. And the goal in designing a hierarchy is to achieve the desired T1, which is the access time at the top, within an allowed cost. Right? You could make the hierarchy a million deep, if you will. You could have a million cache levels, but probably that violates your cost because you have limited space on chip. Right? Ideally, what you would like is T1 equals the access time of this level, right? Level 1 cache. But I mean, we already figured out that that's not difficult. So what do you normally try to do? You normally try to minimize the miss rate at any level. How do you do that? You could increase capacity, but this lowers miss rate, but this increases the time. So you usually use smarter management techniques within the cache, such that you don't significantly increase the hit time, but you reduce the miss rate. And we will see some of these. For example, actually, you will the extra credit assignment you will have is to experiment with some of these replacement or insertion policies into the cache to decide what to keep in the cache and what to cache and what not to cache to actually maximize performance, if you will. Okay, you could do things like prefetching, anticipate what you need and bring the data in to the cache before you need it. And we'll talk about that. Or you could also keep TI low. Basically, you could have faster, lower hierarchies. But again, this could increase cost, right? So if you want to keep the latency of the lower hierarchy, actually I should call higher, really. Latency of the higher levels, if you will, together low, a normal way of doing this is to introduce intermediate levels. That way you reduce the latency of the next level and you have a hit rate and you try to manage the level such that you minimize the misses. So if you look at Pentium 4, I will not go over this a lot, but I'll give you some parameters from, I guess, a reasonably recent processor, but still, how many years old? 15 years old maybe? Or almost 15 years old, at least that's when the design started, right? Well, this is Prescott. This is a 90 nanometer version of Pentium 4, so I'm not that much of a dinosaur yet. So if you look at Pentium 4, you have a D cache that's 16 kilobytes, and its access latency is 4 cycles, for integer operations at least. FP operations take longer because they access wider data. And you have a second level, which is 1 megabyte, and it takes 18 cycles to access. And you have some main memory, which we will cover in a lot more detail. This is just an approximation right now. You've already seen actually earlier in the lectures that when you access main memory, you could get very different latencies depending on whether you get a row buffer hit and row buffer miss. But assume that it's 50 nanoseconds. So you could plug in different numbers to see what is your average access latency. So if you plug in miss rate 0.1, 10% for the D cache, and 10% for the L1 cache, 10% for the L2 cache, you get an average of 7.6 cycle access latency. If your hit rate is 99% at both levels, your average access latency is 4.2 cycles. And you could get different things here. Okay? You could do this. So notice that the best case latency is not 1. So Pentium 4's L1 data cache, you can never, your load to use latency is never 1 cycle. Where is that load to use latency? Why? Because they've designed a very high frequency machine. And they made the trade-off that if they actually designed a cache that takes 1 cycle to access, their miss rate would be unreasonably high. So they will not get good performance. So that would be perhaps like a 4 kilobyte or maybe 4 kilobyte cache, let's say. And that's too small to get a reasonably good miss rate. That's why they decided to go with a 16 kilobyte cache that takes 4 cycles to access. Yes?
Does it always make sense to separate data cache and instruction cache?
So we'll get back to that. This slide is actually wrong. This should be L2 unified cache. So remind me to correct this, please. But we'll get back to that. That's one of the design choices. There's a huge design space in memory hierarchy, a huge and exciting design space. So hopefully, by the end of this lecture, you'll see the trade-offs. So let's take a look at the cache operation. Okay, I'll skip this. So basics. I already talked about a block. A block, or a line you will also hear, is the unit of storage in the cache. This is actually IBM versus DEC terminology. I think DEC uses, Digital Equipment Corporation used cache lines, and IBM used cache blocks. And both terminologies persisted over time. Even within a single document, you will see people using block and line interchangeably. So, as I showed you here, memory is logically divided into cache blocks that map to locations in the cache. And when you reference the data, you get a hit if the block is in the cache, and you use the cache data instead of accessing memory when you get a hit. When you get a miss, then you need to bring the block into the cache. And the entire block is brought into the cache. Which means that you have to kick something else, potentially, to do this, to handle this miss. There are many important cache design decisions, which we will go over. Hopefully all of them today. Placement. Where and how to place or find a block in cache. This is a very fundamental thing. Replacement, what data to remove to make room in the cache. What should your block size be? Should it be 1 word? Should it be 64 bytes? Should it be 1 kilobyte? There are trade-offs associated with it. Should it be uniform or non-uniform? Should you have different block sizes? Well, we'll assume a uniform block size, because non-uniform block size actually complicate the hardware design. But you can stretch your imagination a little bit. This is actually not true for software caches. In hardware, blocks are usually uniform. In software, for example, if you do web caching, you have files of different sizes, right? So you could cache things of different sizes in that case. But in hardware, you want to preserve regularity. Although people have proposed designs with multiple different block sizes too in hardware. Write policy. What do you do about writes? When you do a store, do you bring the entire block into the cache? We'll look at that. And instructions and data that you mentioned. Do we treat them separately? So this is the abstraction of a cache. Basically, you get an address. You need to figure out whether your cache contains the data. So cache is logically and physically divided into 2 things. The tag store, which basically answers the question, is the address in the cache? So you get a hit-miss signal out of this tag store. And it also does some other bookkeeping, as we will see soon, to, for example, figure out or to aid the replacement policy, to keep information about the blocks such that we can decide when we're evicting something what to replace. Data store this essentially stores the cache blocks. So in a sense, most of the intelligence is really in the tag store, right? Because this tells you whether the address is in the cache and keeps track of bookkeeping. And you have control logic somewhere here. So if you actually look at this, I will not go through this, but this is another way of showing the previous equation. You can have, this is the average memory access time. It's the hit rate times hit latency plus miss rate times miss latency. And this miss latency, if you will, is the average memory access time of the next level. I guess I'll give this bit to you, but I will not answer it. Can you think of cases where you could potentially reduce average memory access time, but you get reduced performance? So this is average memory access time is a proxy for overall performance, right? Average memory access time. But overall performance, as we know, is not that. Overall performance is really execution time of the entire program, right? The question is, if you improve average memory access time or reduce that, do you always reduce execution time? So does this always follow? I'll let you think about it. I will not answer this, but the way I asked the leading question, you should think that it's actually reducing average memory access time actually can reduce performance. And think about it. Okay? Okay, well, so let's see how this cache actually operates. We have this memory divided into cache blocks, and each block maps to a location in the cache, determined by the index bits in the address. So I'd like to keep that memory over here, actually. But you have an address, and this address is divided into three things. The bottom bits specify the byte in block, right? So in this case, what I'm showing you here is an 8-bit address, and byte in block is 3 bits, which means that the cache block size is 8 bytes, right? Let's say we have a cache that has 8 byte blocks. You need 3 bits to specify which byte in the block that you're accessing, right? And let's say our cache is cache has I guess in this case 8 locations, if you will. I guess I'll show that to you. So this is your index, if you will. So you have 3 bits to specify which location in the cache does this address map to. That's the notion of the index bits. Each block maps to a location in the cache, and this is determined by the index bits in the address. And the number of index bits is determined by how many locations are in the cache. I'm assuming something here which will become clear later on. That's not necessarily true. But you use these index bits to index into the cache structure. So let's say this is your cache. It has 8 possible locations. 1, 2, 3, 4, 5. Is that 5? 6. Hopefully that's 8. You use 3 bits to choose where the block can go. Right. So how do you access the cache? Basically, let me divide this into the tag store. You index into the tag store with the index bits in the address. And, well, this doesn't work out well. Let me see that? There it is. Let's create some space for other logic. Okay. You access the tag store, and also you access the data store in parallel. So we have 8 possible locations of the cache. 6, 4, 5, 6, 7. Okay, there you go. And then we also use this index to index the data store. Again, data store corresponds to the tag store, but this just stores the data. Five, 6, 7. And from this cache, we said 8-byte blocks, so each of the data store entry is 8 bytes, if you will. So by indexing, remember this is a memory bank that I showed you before. What does this indexing mean? You decode the address and get the data out. Let's assume that your row is 8 bytes. So once you index, what you get is you get the data out, and you also get a tag store entry out. This is the tag store entry. And tag store entry contains two things, really. It contains, well, maybe I'll show it here. It contains one bit saying whether the data is actually valid, whether you brought something meaningful to that location in the cache. And if the data is valid, what is the tag of the data? What is the remaining part of the address of the data? Right. Because you have limited cache space, your memory is much, much larger, right? And you're using the index to index into this tag store. Now you have to also determine whether the thing that's stored in this tag store in the cache is actually the thing that you're looking for. And that's the purpose of these tag bits, the remaining bits in the address. I guess in this case it's 2 bits because we have an 8-bit address. Basically, when you do a cache access, you index into this tag store, you get the valid bit and the tag associated with the data. And if the tag store entry says the entry is valid, that means the data, there's some meaningful data here. The hardware compares the tag that's stored with the tag of the address. If they match, that means that the data that has been stored in this location is actually the data you were looking for. Right? If they don't match, then that's not the data you're looking for. Okay? So that's how you access the cache. Okay, if the block is in the cache, which is a cache hit, the tag store should have the tag of the block stored in the index of the block. So basically, what you have is a comparator here that compares, well, the tag that's stored in the cache with the tag of the address that you're accessing. And if this is true, like hit, let's say, and if the valid bit is set, well, let me call it a tag match, not hit yet. If you get a tag match and the valid bit is set, then you get a hit. Right? Now, if you get a hit, then the data that you've concurrently accessed with the tag store is the data that you want. Otherwise, it's not what you want. Okay, so let's take a look at this. So this is the memory that I've constructed, if you will. We have the same address. It's 8 bits. And we have 8-byte blocks, which means that in memory, in the entire memory, you have 32 blocks, right? I guess I could do this, but it'll take a while. Instead, I drew that over there. Let me do this in a relatively sloppy way, but you can follow it over there. So what does this mean? You have 32 blocks in memory, logical blocks in memory, but your cache can store only 8 blocks. And a block can go to only one location, right, in the cache. Remember, the location a block can go in the cache is determined by these index bits. And only one block can be stored in that location. We'll call this a direct map cache. Basically, any block that maps to the same index, or out of all the blocks that map to the same index, you can store only one. Right? So you can see that this is a problem, right? Here I have highlighted blocks 0, I guess this is 8, 16, and 24. they all map to the same location. 0, 8, 16, 24, and stretch your imagination such that the memory is bigger. These have to map to the same location. Well, I guess there's more, right? Because these all map to the same location because, no, that's all. Yeah, because it's a 32-byte memory, 32-block memory. These all map to the same location because they share the index bits, right? They have the same index bits. So if you look at address 0, what you have is index bit 0, 0, 0, your tag is 0. And I'm going to omit the remaining. If you look at address 8, this is your index and tag. If you look at address 16, your tag is 10, index is, if you look at address 24, your tag is 11, index is 0, 0, 0, right? Which means that you can only store one of these in the cache at the same time. Now, could this be a problem? If you need both of them at the same time in the cache, this could be a problem, right? So why could you need both of them at the same time in the cache? Well, think about a loop, for example. You're executing a program, and you have a loop, a while loop. And it turns out, in all iterations, you need two values, A and B, and you do something with A and B. Maybe not A plus B, but you add A to some blah and B to some blah, and you compute x plus y and result store the result in some blah array. So in all iterations, you access A and B. You really want these A and B in two different cache blocks, such that you always hit in the cache when you access them. But if it so happens that this A maps to location 0 here is stored in location 0, and this B is stored in location 8, well, let's not store them in the same location. This is address 0 and address 8. You'll get misses for both of those locations, right, when you access it. So this is called a conflict miss, and this happens because multiple, the blocks that share the same index map to the same location in the cache, and you can only store one thing. Make sense? So that's the problem with a direct map cache, because you have one index that can store one entry, and this is the example that I showed you here. This can lead to 0% hit rate if more than one block is accessed in interleaved manner. And this is what's happening here, right? If you look at the access pattern here, at least to cache index 0, you get A, B, A, B, A, B, dot, dot, dot. So the first time you access A, you store A in the index. The next time, in that set, if you will. The next time, you need to access B, but B is not in the cache, so you evict A and store B. The next time you access A, so you need to evict B and store A, and then you need to evict A and store B, so you get 0% hit rate. Okay, and these are all conflict misses. So you could actually solve this problem, and that's the idea of a set-associative cache. What you could do is to organize your cache such that it doesn't look like this. So here what we did was, okay, because if I push this harder, it will go up higher. Okay. Here in our cache, what we had was really a single column that contained 8 different, we organized the cache as a single column that contained 8 different sets, if you will. But we could organize the cache in a different way. Instead of having a one column of 8, we could have 2 columns of 4 blocks. Right? Meaning that we could change this. Let's see. I don't want to lose that much, but okay. That's fine. I guess you guys remember that, right? Now, for each index, we can have the ability to store 2 different blocks, if you will. But we have fewer number of indices, if you will, in the cache. So instead of that single column of 8 indices, we have 2 columns of 4 indices, but these could store independent things. So we've divided our tag store and the data store. Now in the tag store, for each index we can store 2 things. We have one valid bit and tag, and for the second thing we have another valid bit and the tag. And we have 4 of these, if you will. Okay? And I will not draw this more here, but that's the idea of a set. A set is the set of all blocks that share the same index. Right. Now how do you index into this cache? What has changed? This is your address. These bottom 3 bits still tell you byte and block, but now we have 4 sets, if you will. So we use only 2 bits to index into the cache. And the remaining bits are actually the tag bits. So now what we do is we index into both ways. These are called ways. Way 0, way 1 in the cache. And get both tag store entries that map to the same index out. Which means that we get the tag out and the val bit out. And we get the val bit out and the tag out from the second column, if you will, second way. And we need to compare the tag to both of these, because now the locations that share an index in memory can go to 2 places, right, in the same set. Okay? Now your val bit logic becomes more complicated. So you can get a tag match in way 0, or you can get a tag match in way 1. And you get a cache hit if there's a tag match here and the data is valid, or if you get a tag match here and the data is valid here. Make sense? Okay. And of course, once you get the hit, you need to select, well, let's just go through this, I guess. At the same time, you index both of the data stores, if you will, and get the data in both of the ways. Data in way 0 and data in way 1. And you need to figure out now which data to pick, actually, right? This is really your output data. And that depends on which way you got a cache hit on, right? So this will tell you the way that you hit in. So there's some logic here that I'm not going to draw. Actually, you should be able to draw this logic that tells you which way you hit on. And that's very simple, right? If your tag matches in one way and if the valid bit is set, you hit on that in that way. Right? Okay? Does this make sense? So now what we have is the ability to store 2 of these green ones, if you will, that happened to map to the same index previously, and we couldn't store them because there was only one location in that index. Now we can store 2 of these together, potentially. So if we're accessing A and B, and they happen to map to the same index, now we can have both of them in the cache. Right? That's the advantage. That's the idea of set associativity. This is a 2-way set associative cache, which means that in a set, you can store 2 different blocks with the same index. Advantages, you have fewer conflict misses. Disadvantage, well, obviously this is more complex, right? Why? Well, there are 2 reasons. One is, this is now set associative. Before, we did not have any associative logic. We had one comparator here, right? Now we have to do 2 comparisons in parallel. Plus, we have to do muxing to determine which data to get out of the data store, because there are 2 ways in the data store. So this takes longer to access. It's slower to access, you get a larger tag store. Well, why do you get a larger tag store? Well, one of the reasons is tags are larger also, right? For the same size cache. Because what you've done essentially is you reduce the number of indices by laying out the cache in a different way logically. Okay, so you could imagine, now let's take the exercise further. What if you had 3 things that actually map to the same index? This doesn't solve that problem, right? What if you had A, B, C, and they all happen to map to set 0, and you access them in a cyclic manner? A, B, C, A, B, C, A, B, C, A, B, C, A, B, C. Well, you get all cache misses again, right? How do you solve it? Well, 4-way associative cache. Right. Now you have 4 columns of 2 blocks each. And it's the same idea. Likelihood of conflict misses is even lower in this case, but now you have even more tag comparators and an even wider mux to mux out the data from the data store. And in even larger tags, right? Now you have a single bit to determine your index. Well, you could take the concept to the extreme and have full associativity. This is the most permissive cache organization, if you will, in the sense that a block can be placed in any cache location. What we've done here is we've gotten rid of the index bits, right? This is purely content-associative memory now, right? When you're searching for a block, you basically check the tag of each location. Each block location in the cache, tag store is essentially, each block has its own tag in the cache. Blocks don't share tags, if you will, because they happen to map to the same index, because there is no indexing. Make sense? So the downside, obviously, is now you have a huge number of comparators. Now, here we had only 8 blocks, but think about having 16,000 blocks in a large cache. You want to have 16,000 comparators. Probably not. Okay. So associativity is how many blocks can map to the same index or set. So is this all clear? How you access a cache and what do you compare? You knew all of this before? Really? Okay, let's go faster then. Okay, how many blocks can map to the same set or same index is the idea of associativity. Higher associativity in general leads to higher hit rate. That's not always the case. In fact, there are cases where you could get lower hit rate with higher associativity potentially, but that requires some access patterns to think of. The downside is slower cache access time. Why? Because your hit latency increases. Why does it increase? Because you need to determine whether you hit or not, you need to do multiple comparisons and figure out which one. Also, the data access latency increases because you need to mux out the data from the ways. And it's more expensive hardware. Usually you get diminishing returns from higher associativity, and this is a common curve that you see. Going from 1-way to 2-way buys you most of the performance benefit of associativity. And 2-way to 4-way, you get less performance, but still reasonable. But going from 32-way to 64-way, you don't get that much performance. You eliminate those cases where you get bad conflict misses because you have a large cyclic reference pattern, if you will. Okay. Okay, we already talked about this. So once you have an associative cache, you have the question, which block in the set to replace on a cache miss? Now, this is not a problem in a direct map cache, right? Because in a direct map cache, you have only one block that you can replace. So you have to replace that one. In a sense, your decision is, do you actually cache this thing that you're accessing or not? But we're not going to cover that for now. We're assuming that anything we access, we're going to cache. So normally, well, if there's an inval block in the set, you first populate those blocks. Right? It doesn't make sense to underutilize your cache. Keep some ways invalid, if you will. But if all are valid, now you need to design a replacement policy. And one replacement policy could be random. Right? You could pick randomly which way to get rid of. In fact, it turns out this performs as well as some potentially more reasonable policies that you think of. People have done studies with this, and it turns out random, on average, across a large variety of workloads, performs similarly to least recently used. And we'll see why. Because least recently used has a bad problem with some kind of patterns. Other policies, you could do first in, first out, right? And it turns out this doesn't perform very well. Basically, the first thing that comes into the cache, you keep track of what is the first thing you brought, what is the next thing, what is the next thing. And it's like a first in, first out. And it doesn't work too well. Least recently used, basically, we'll talk about this. You like the FIFO or the random? This has actually been a topic of study for a long amount of time. People are still studying these things.
Is FIFO ever useful?
Is FIFO ever useful? Well, I guess that could be your homework question. That could be a homework question. You could find perhaps access patterns that are useful, that work. Access patterns for which FIFO works better than LRU. So these different policies work well for different access patterns. And you could come up with some access patterns where FIFO is good. Least recently used, basically you evict the block in the block that's least recently used within the set. And we will cover this in more detail. You could have other policies like not most recently used. And this is actually proposed because least recently used is hard to implement. And we will see why. You could have least frequently used if you keep track of the frequency of the blocks. Or other more innovative policies, you could have policies like least costly to refetch. Why? Because memory access could have different costs, right? And we've already talked about this before. Why would this happen? Like one memory yeah.
Well, if you have multiple caches, something could be in L2, and something else could have to be in main memory, right? So
that's right.
You might want to replace something that's closer, so you don't have to.
That's right. Yeah, that's a very basic one. For example, if you know that the thing is in the block you're accessing is in L2 versus main memory, that's a big cost difference, right? Latency difference. If you could know that, of course. There are other reasons. For example, you could be caching data that's actually in a remote memory, in a different processor. We haven't covered multiprocessors yet, but you could be caching data from a different processor's memory. That's usually very slow to access. So you might want to bias your policies such that you try to keep those in the cache. But of course, if you just do this, it's not good, because what if you're never going to use that data again? So you need to have a balance between recency and cost, if you will, and potentially frequency. Okay, there are hybrid replacement policies also that try to combine some of these, because there needs to be a balance. What about the optimal replacement policy? I guess we'll get back to this. I guess what is the optimal replacement policy? Never have to replace. Well, that's too good. Optimal is you really would like to figure out what it is among the set of blocks that you have is going to be referenced furthest into the future, and you'd like to replace that one. Right? But how do you know that? Well, that's tough. Right? That's why it's optimal. So it's an unrealizable optimal. Okay, we'll get back to this. So let's look at LRU, though. This is the most commonly used policy. The idea is simple. Evict the least recently accessed or least recently used block. The problem is now you need to keep track of access ordering of blocks, right? You have to have an order. Not only, you cannot just keep track of the whatever is accessed last. You have to really have an order of what is accessed between the blocks that you have. Okay, here's a question for you. Let's say we have a two-way associative cache like this. What do you need to implement LRU? Each set has two blocks, and you need to figure out which one is the least recently used. 1 bit, right? You basically have 1 bit in the tag store that says it's either way 0 or way 1. And when you get an access, if this says way 0 is the least recently used, evict that one. Okay? What about if you have a 4-way associative cache? What is the minimum number of bits you need to encode the ordering? Minimum number of bits. Yeah?
You just need to know which particular one was the least recently used, so you keep track of that index.
But you need to have an ordering, right? once you eliminate that, let's say once you got rid of that, now what is the least recently used? So you really need to encode the ordering. Any guesses? So, okay, so you have 4 ways. 1, 2, 3, 4. 4 possible blocks. And if you think about it, any 4 of them could be the least recently used, right? And once you determine what's least recently used, you have 3 things that could be next least recently used. And once you have those 2 fixed, you have 2 things that is next least recently used. And then you can have only 1 thing that's most recently used. So it's really 4 factorial different orderings. Right? Is that, yeah, 4 factorial. Is it 6 bits, 4, 3, 5 bits? Right? Yeah, so to encode which ordering you have among these 4 blocks, you need to encode, I guess this is 24 possible orderings, which means that the minimum number of bits you need is really 5, right? Which is the log 2 of 24. Yes?
You go over that again.
So, okay, how many different orderings are possible for 4 blocks in the cache in terms of access order? So, any 4 blocks can be the least recently used block. Once you set that, now you can, among the remaining 3 blocks, any 3 block can be the next least recently used. Among the remaining blocks, 2 blocks, any 2 block can be next least recently used. And now you have most recently used, only 1 block can be most recently used. So in a sense, you have these bins, and 4 things can go to the first one, 3 things independently can go to the next one, 2 things independently can go to the next one. So you have 4 times, 3 times, 2 times 1 possibilities. How do you encode it in 5 bits? Well, for each different possibility. And now how do you decode it is the harder question, right? Now when you try to figure out what to determine, basically these 24 possibilities tell you what is the ordering among the 4 different ways that you have, right? So you need to decode this to figure out what is the least recently used way. And that decoding logic becomes complex. Make sense? So if you want to design a true LRU, if you will, true LRU is something that truly maintains this ordering, or sometimes it's called perfect LRU, it becomes complex. And this is only for a 4-way cache. What if you have an 8-way cache? Then you have 8 factorial orderings, right? And if you have 32 ways, 32 factorial. So it becomes impossible quickly. Well, nothing is impossible, but if you don't want to build hardware for this, I would say. Okay. What is the logic? We've already talked about this. So the logic that's needed to determine the LRU victim for this is decoding. Of course, you could spend more bits to make the decoding simpler, right? But then now your area overhead to just keep track of the replacement policy increases. Even 5 bits is, you essentially have a 5-bit entry into your tag store, right? To perfectly encode. Okay, so because of this, most modern processors do not implement true LRU. It's complex to do. Well, this is one of the reasons it's complex to do. Second, LRU is an approximation to predict locality anyway. As I told you before, random performs on average as good as LRU on average. So you don't really need to be true to LRU, if you will. You could be a little bit approximate. What are examples of this? Not MRU. That's a very simple policy, right? You basically don't evict the most recently used block. And you could keep track of what is the most recently used. I guess I'll let you figure out how many bits you really need to do that. I'm going to say 1 bit per block, but actually you could do better. I'll go over 2 different policies. These are actually fun policies that people have developed. Hierarchical LRU is one of them. Basically, you can divide the 4-way set into 2-way groups and track the MRU group and the MRU way in each group. Right. This is actually implemented in quite a few processors. Let's see how much time do we have. Well, we still have some time. Or the second thing that's also implemented is victim next victim replacement. You keep track of only the victim and the next victim, if you will. Which means the least recently used and the next recently used. And the rest is just random. So how do these work? I guess I've already drawn you this. If you have a hierarchical LRU, let's say you have a 4-way cache, you can have 2 bits for replacement for each way. One bit says, is this the MRU group? And the second bit says, is this the MRU block within the group? So basically we divide the 4-way cache hierarchically, if you will. 1, 2, 3, 4. And let's call it group 0 and group 1. And we're going to keep track of whether group 0 has the MRU position or group 1 has the MRU position. And within each group, we'll keep track of 1 bit for each. So each of these blocks, if you will, have 2 bits dedicated for this. So this is just an example. I guess I'll walk you through it over here since I've already done it. So this is the first group. This is the second group. And let's say you have A, B, C, D store. And let's say this is your initial state. What does this mean? Basically, the MRU block was within this group. That's why you have 1, 1. And the second bit specifies the LRU block. So this is the LRU block. And here, you know that this group does not contain the MRU block. Okay. Let's say you have an access to B. What happens is this group still remains the most recently used group. That's why you have 1 in each bit. But you just flip these bits within the group, such that now you know that this is the most recently used. Right? And you don't do anything around here, because you hierarchically divide it, your set. And you could imagine doing this for a larger number of levels, if you will. Now you have an access to D. What happens? You determine that D is within this group, so you reset the group MRU bits for the blocks within group 0. That's why you get zeros here, and you don't touch these bits. And now you set the group MRU bits for C and D, which are these top bits. And because you're accessing D, you set the MRU bit for D. And let's say you have an access to X after this. Well, victim is now easy to determine, right? Whatever has the 0, 0 value is the victim. Because it's not in the MRU group. It's also not MRU within the group, if you will. So now you replace A, and now this becomes the MRU group. That's why you set the MRU bits within the group, and you set the MRU bit for the particular block as well. Okay? And then you reset the MRU bits for the other group, if you will, for which you didn't touch the block. Make sense? This is one approximation. Well, I guess this could be a homework question potentially, or even an exam question maybe. You could come up with an access pattern in which the scheme would have 0% hit rate. I think that's relatively easy. The harder one is come up with an access pattern for which the scheme performs worse than true LRU. Remember, we're trying to approximate true LRU. Or you could come up with an access pattern for which the scheme performs better than true LRU. And all of these are actually possible. The easy one is 0% hit rate. Right?
How is this not true LRU? Doesn't it work
That's a good question. That's what you should think about. This is not true LRU, right? Because you don't have the full ordering.
So you have this.
It's all hierarchical. Okay. Okay, next victim policy, I'll cover this very quickly also. Basically, you have 2 bits for each block that basically say, is this block the victim or is this the next victim? It cannot be both. But it can be neither. That simplifies some things in this policy. When you get a cache miss, you replace the victim and promote the next victim to victim. And you flip a coin to determine which block will be the next victim. So you randomly pick the next victim. When you get a cache hit to victim, the victim becomes nothing, if you will. You zero out the bits. it becomes neither victim nor not victim. And not victim becomes promoted to victim, and you flip a coin to determine the not victim. When you get a cache hit to not victim, not next victim, if you will. Did I say not victim here? It should be next victim. Then next victim becomes nothing, because you don't want to evict it right away, right? And you flip a coin to determine the next victim. So this is pretty simple, but just to give you an idea, let's say your A is the cache block at A is victim, and C is the next victim. Then B and D are nothing essentially. When you get a hit to A, you reset the bits, victim and next victim. You promote the next victim to victim. That's why C becomes 1, 0. And then between the remaining ones, you randomly pick one to be the next victim. So this is very simple to implement also. And you can have the same questions as before. Okay? So set thrashing, this is the reason really random works better than LRU in some cases. The idea of set thrashing is you have the working set of the program for that set, if you will. These are the elements that you access that happen to map to the same set within a given interval of time. And that working set could be larger than your associativity. Remember, we wanted higher associativity to prevent this case. Well, we cannot have a lot of associativity. So let's say you have cyclic references to A, B, C, D, E. And they happen to map to this four-way thing. Forget about the replacement policy now. We could have true LRU. A, B, C, D, E. And you repeat this. If you use LRU, you get 0% hit rate, right? Because by the time you access A, you already brought B, C, D, E into your cache, and they've occupied all of the four ways. Well, if you add random, it's likely that you'll keep A in the cache. That's why random does better. And I'll let you calculate the probability that A will be in the cache the next time you see it with a random replacement policy. In practice, well, this depends on the workload. An average hit rate of LRU and random are similar. And it's similar because there are quite a few workloads that exhibit something like this or something similar to this. And on those workloads, random replacement policy actually does significantly better than LRU. So in a sense, if this is your access pattern, what you really want is to say, okay, I'm going to cache only these, and they'll remain in the cache, right? Then you really get 80% hit rate in this access pattern, right? So you could do better than random in this case if you're smart enough to detect this access pattern. And people are proposing optimizations, and some of which are implemented, that try to detect these patterns and cache things better. Of course, this is all dynamic in hardware. It's transparent to the programmer, right? If the programmer needed to do this, they would go crazy. Okay? You could have hybrid of LRU and random, and that has also been proposed. I will not go over this. So let's go back to optimal. I already talked to you about this. This is actually called Bellity's optimal, owing to Bellity from 1966, who studied the replacement algorithms for actually page management between DRAM and disk. In sense, DRAM is a cache for disk, right? So you have all the same issues at that level also. So his optimal was to replace the block that is going to be referenced furthest in the future by program. And I guess my question to you is this optimal for... Well, first of all, how do we implement this? Well, you cannot implement this. You have to really predict what is going to be referenced furthest into the future by the program. And if your prediction is 100% accurate, then you've implemented it. But that prediction is hard to get 100% accurate, I would contend. Even simulating this is very hard. And I'll let you think about how to simulate this. Okay, so is this optimal for minimizing misrate? It is, right? If your goal is misrate. But again, let me challenge this goal to you, because performance, again, is not misrate. Average memory access time is a better metric, but performance is, again, not average memory access time. Performance is execution time. Okay. So is this optimal for minimizing execution time? And it turns out it is not. Because cache miss latency or cost varies from block to block. Right? And we've already discussed many different reasons for this. You could have remote versus local caches. You could have overlapping of misses. Not all misses take the same amount of time. You could be prefetching one miss, and when the processor requested that block, that prefetch may be halfway complete. Right. We didn't cover prefetching, but prefetching is the idea of generating the request before the processor needs it. Okay? And this paper that we had written a while ago showed that actually with these, when you take latency into account, this is really not optimal. So optimizing for this may be optimizing for the wrong thing anyway. So I think this is good to keep in mind. When you have out-of-order execution, for example, when you have multiple outstanding memory requests, not all cache misses have the same cost also. Because one cache miss, while you're waiting for one cache miss, you could have generated another cache miss, right, in a superscale processor. And the latency of the second one could be hidden. Because by the time you service the first one, the second one is complete. You can never see that latency because you're doing out-of-order execution. Okay? Okay, so let's circle back a little bit. What's an attack store entry? Just so that you get these right. You need a val bit to say whether this data that this tag is associated with is meaningful. You have a tag, you have some replacement policy bits, and you have something called a dirty bit, potentially. Dirty bit, if you have it, specifies that you've written to this cache block, and the cache block is different from what's in memory. Of course, you need a dirty bit only if you're writing to the cache block but not writing to memory. Right? That's the notion of a write-back cache. If you have a write-through cache, you don't have this problem. Whenever you're writing to a cache block, if you also write to the memory, then that's a write-through cache. Basically, when do you write the modified data in a cache to the next level? If you do that at the time when the write happens, it's write-through. Otherwise, it's write-back. When the block is evicted, it's write-back. Basically, you need to keep a modified bit in the tag store indicating that the block is modified if you have a write-back cache. The advantage of this, well, this is the downside, right? There's an extra bit. The advantage of this is now you can consolidate multiple writes to the same block, right? You don't need to do all of the writes. All of the writes don't need to go to memory. But you could be doing this. This is your cache block. You could have a store to the first word, and then you could have a store to the next word, store to the next word, store to the next word, store to the next word. And if you have a write-back cache, none of these need to go to memory individually. Right? You could do all of these stores in the cache, and when the block is evicted, you write back the entire modified cache block. That's the advantage. Bandwidth savings. You save the bandwidth. Write-through is, although simpler, you don't need to have the extra bits. All levels become up-to-date. There's no consistency issue, if you will. Your level 1 is the same as your level 2, is the same as your level 3, is the same as your memory. Of course, the downside is it's more bandwidth intensive. You don't coalesce the writes. Okay, next time we'll pick from here and consider more issues with writes and caches.